Please go on with your presentation.
I hope you can see my slides and you can hear me clearly.
Yes, yes.
Okay, good. Good afternoon, everybody. I am Sri. I'm a doctoral researcher at the University of Luxembourg. Today, I am going to present how to retrofit legacy machines in the context of industrial Internet of Things. So this is the agenda for my presentation today. I have 6 topics to talk, from the introduction to summary. Let's start with the introduction. We have done a survey in the first year of my PhD with the consortium of, you can see the pilot project, where the SMEs are interested to adapt to industrial Internet of Things, but they have no idea where to start and how to start. So we have formulated 3 questions about that. Are the SMEs actually data ready to enter the prism of industrial Internet of Things? And how to empower them towards Industry 4.0, and what are the basic steps towards a connected enterprise? So these are the questions that are still unanswered in the literature, but in our background survey, we found that SMEs are neither data ready nor ready to adopt industrial Internet of Things in their existing operations. So how many companies we did the survey is around 100 companies. So that is enough data to conclude those things. So based on this information, we wanted to make them data ready. So for that, we have 2 options. One is to buy advanced machines for SMEs, and the other is to upgrade the existing machinery. That's where the concept of, we chose the later, that's where the concept of retrofitting come into picture. Retrofitting is an action to upgrade your existing machinery or to update or refurbish it. So how to upgrade is by retrofitting external sensors or adding any softwares if necessary, or and this has to be very inexpensive because it is an SME, and also it has to be easy to use. What are the advantages by retrofitting your legacy machines is that this is the starting point for your transition towards smart manufacturing from a traditional manufacturing. And this is a least financial effort as well, with the less time expenditure, and also the risks involved in retrofitting are very low. Last but not the least, but there are some challenges involved in this process, which sensors to use. And also there are several communication protocols exist, but SMEs have no idea about how and which one to adopt. And also to protect SMEs from the external attacks and threats. This is also a challenge. So these are the things that we are going to address in today's presentation. However, before that, I would like to mention few state-of-the-art literature that we found interesting and relevant to this study. The first one are proposed by Zambeti et al. And she proposes there are 2 reasons why industrial Internet of Things there are 2 drivers for industrial Internet of Things in the enterprises. First one is the push from the buzzword called Industry 4.0 itself, and the second one, there is a need, so that they're pulled by the need. So I present 3 more literature here. So first one is about need-based pull, so predictive maintenance using retrofitting a robotic cell. So here the researchers retrofitted a robotic arm so that they can maintain the robot when it's before it's too late and before it's breakdown. And the second work is a holistic approach. It's mostly inspired or driven by Industry 4.0 push. So the company here did the total transformation of the enterprise, especially in the aspects of maintenance and operational safety. And the third literature is a review study where the researchers presented industrial Internet of Things and the technologies that are essential to adopt industrial Internet of Things in a company. However, there are gaps that we found in this state of the art. First one is clearly these are the focus on small and medium scale companies are clearly missing because they have a different starting point when compared to the larger companies. What is prevalent in this existing research is what they have done, technically, what they have done is very prevalent. However, how they have done is not very much focused. Therefore, we thought of creating a basic architecture for industrial Internet of Things. Of course, that is in the context of retrofitting. And we also wanted to validate that basic architecture using laboratory as well as field tests. I jump into the architecture that we proposed in the paper. We have created this architecture in 3 layers: the physical layer, IoT layer, and the cyber layer. Let's dive deep into physical layer. What contains the physical layer? At the beginning of the retrofitting, you do not have any infrastructure other than the machines. So the machines are legacy machines, and they have neither data connectivity nor have the capacity to generate to transmit the data. Therefore, the first thing is to retrofit sensors to the existing machines. So they also fall under a physical layer. The next step is an optional step, is an IoT device, adopting IoT device. They are non-standard devices that can connect to your network and have the capacity to transmit the data. However, a good example of an IoT device is your mobile phone itself. However, it is an optional step, and it is very useful if a company wants to digital transform the whole enterprise. So it comes handy. And then with a field bus, we connect to something called IoT nodes. These are the critical points in the architecture because the IoT nodes are where the data gathering happens. And from those IoT nodes, we can have PLCs, microcontrollers, edge devices, or a normal computer for the IoT nodes. And from there, we connect it to a communication protocol. The communication protocol could be OPC UA, which is widely accepted, or simple Ethernet connectivity. So from there, we jump to the IoT layer. In the IoT layer, we have 2 important things. One is IIoT gateway, where we include the security aspects of the data, data gathering, processing, and delivering. And then you have IIoT middleware. This is very important. This is where we connect your physical entities to the cyber entities. So physical entities, so for example, sensor data can be fed to IoT middleware. With a simple JavaScript, we can convert that to understandable units and then push them to the databases. Finally, we have a cyber layer, which includes a database. And this database could be local as well as a cyber. So some companies prefer to have the database locally to avoid threats from external hackers. So we have, in our field test, I will show you, we adopted a local database. However, you can also have a cyber database. And this database, from here, you can send the information to analytics, monitoring, etc. So here you just add on the applications. This is the general architecture in the context of retrofitting. Now I will show you the laboratory implementation. We have, to implement it in the laboratory, we have taken a drilling machine that has no sensors attached with a maximum RPM of 3200. And then another hardware we chose was Raspberry Pi. And we also added a few things to the Raspberry Pi. One is touchscreen to be able to interact with the Raspberry Pi, and then an analog to digital converter in the form of a Pi hat. I will let you know more about why we added analog to digital converter. Before going deep into the architecture for laboratory implementation, what to measure from the drilling machine. So we have chosen to measure speed of the drill as well as the drill depth as a critical variables. To measure speed, we adopted a Hall sensor. So you can see a Hall sensor. It has a 5 volt input, however, to connect it to Raspberry Pi, we needed to convert that 5 volts to 3.3. Here we adopted a voltage divider and converted it into 3.3 voltage digital. So it's a digital output, so we can directly connect it to our Raspberry Pi. However, when it comes to infrared sensors, this is to measure the distance or the depth in our case. It can measure from 10 centimeters to 80 centimeters with the highest accuracy. However, this is an analog sensor. This is not a digital sensor. That is why we had to adopt an analog to digital converter. So these are very details. For SME, it might be a bit difficult to get into these details. That's why the upscaling of SME employees is very important. So analog sensor, and then we convert it to digital output using A to D pi hat. The another software we used here, coming to the softwares, we used Node-RED, InfluxDB, and Grafana. These are the three softwares we used, all open source. There are no cost involved in this. So, and Node-RED, as I said, this connects your physical layers to the cyber layer. So it reads the sensor information, transforms, and saves or pushes it to database. And the database we used to collect the data is InfluxDB. It's an open source database as well. And then from the database, we send that information to Grafana. It's a visualization tool, very versatile and flexible tool. You can program the way you want and what the data you want to see, and you can also create alarms when a critical variable is going above the threshold. So this is how the interface of Node-RED looks like. You take the information from Raspberry Pi. So for example, here we are taking information from pin 7. Of course, we are getting frequency, which means that we are measuring speed here. So the function here helps you to program in a JavaScript to convert the frequency to speed, and we push that information to InfluxDB. The same with the distance as well. The function here we coded in order to measure, in order to get an output that is understandable, like speed in RPM and depth in centimeters. Experimental setup in the laboratory has few changes because we figured out that we could install Node-RED in Raspberry Pi itself. We don't need, for example, if you see before, we mentioned it in the IoT layer, but this architecture is quite flexible. So when it was permitted to us, we install Raspberry Pi and we install Node-RED in the Raspberry Pi itself in order to reduce the complexity. Other than that, it looks quite similar to the architecture I proposed. And the results and field test, what we have achieved by using this architecture and doing the laboratory test, we were able to gather real-time information about the machine, especially in terms of speed and drill depth. Of course, we also pushed data successfully to the databases. This was very cost effective because we used open source softwares and sensors weren't too expensive. And then we validated the basic architecture in the laboratory. However, this has come with some challenges. The concept was relatively new, so that there was no standard way of doing things. So we had to create a way that we felt was standard. And the next problem came when we could not find the combination of hardware that can function together. This is a challenge. Even in large companies, sometimes not all hardware speak to each other. Therefore, you need to improvise here. So the improvisation using, for example, where we use JavaScript so that we have an output that is understandable to us. And selection of critical variables. For example, in drilling machine, it's easy. You select speed and drill depth. But however, if you have a production machinery, you have many variables, and selecting few among them can be a challenging task. In the field test, this we did not write in the paper because the field test happened in between July and September. That's why, however, it's finished now, so we can present. As I said, in the field test, we adopted a local database for a quick information gathering. However, we connected that local database to MySQL because the company was using MySQL software. And also you could see we also adopted a Siemens Semantic IoT 2000 as an IoT device so that it includes security aspects of it. In the communication protocol, the company was using S7 communication, which is from Siemens. So we adopted the same. And to summarize, we created a general architecture for IIoT in the context of retrofitting. This applies to the legacy machines and a critical focus on SMEs. And the architecture is adaptable for different machines with slight modifications. I have shown you two modifications of the architecture in my presentation, one for laboratory and one for the production scenario. And this has been validated in the laboratory as well as the company. And we also disseminated the knowledge on how to IIoT ready in this, which is very interesting to SMEs. And we have presented the challenges encountered during the research and how we tackle them. with this, I would like to thank you, ISM organizers, for giving me opportunity to present this. And if you have any questions and want to collaborate, you could contact us here. And we thank ProPilot project and the support given by Interreg 5 program in this to deliver this research. Thank you everybody.
Thank you, Sri, for this really interesting presentation. Is there anyone that wants to ask some questions?